let me start with a motivation of why random matrix theory may be something useful to think about. So we have a network output, which depends on the input X, but also on the network parameters. And for instance, at initialization, there's a probability distribution of these parameters. And as Jim explained last week, this probability distribution can be used to define correlation functions, and one can even think about these correlation functions being part of field theories. So I just want to use this, that ensembles of networks are something to think about, and that they are characterized by a probability distribution for the parameters in the network. For instance, at initialization, this probability distribution may be a Gaussian distribution or a Gloraux uniform distribution, but one can also think about a late phase of training where the network may have settled to a possibly local minimum, but there are fluctuations around this minimum, and it turns out they can be characterized by a power law distribution of variances when performing a eigenvector decomposition of these fluctuations. And this late phase of training would be an example where one can imagine that the empirical weight matrix, which is found in a neural network, consists of a signal part denoted as W0 here. And I will argue that the signal part may have a low rank. And on top of that, there is a random perturbation, which characterizes the SGD fluctuations around this local minimum. And this random perturbation is then characterized by a correlation matrix. So this was an ensemble point of view, but it turns out that even for an individual member of this ensemble, so that would be an individual weight matrix, there are statistical properties like the singular value distribution, which are self-averaging, which means that one doesn't have to perform this ensemble average by integrating over all possible parameter values, but that even a single representative from this ensemble may have statistical properties which allow us to gain information. So I'm going to spend a little bit explaining the data set and the network structure, because in the end it turns out that the specifics of the training algorithm and so on do matter for the results one obtains. So we used for this first analysis the CIFAR-10 data set and used multi-layer perceptrons with 3 hidden layers. So most of the data I'm going to show in the first part of the talk are for 3 hidden layers with a size of 512 each. Then we have an activation function which processes the information from layer to layer. So for the hidden layers, it's the ReLU activation function. For the output layer, it's the softmax activation function. And we use a coarse entropy cost function for training. So all of this is pretty standard.
So specifically, Bernd, you're not using convolutional layer?
I will talk about convolutional layers a bit later, but the first examples will be for these multi-layer perceptrons. And it will turn out that results for convolutional layers are quite similar to these results here. So this network works reasonably well. It has a test accuracy of about 55%. It's not great, but we did train a convolutional network as well to confirm that these results are robust. So that's a detailed list of the networks. So we looked at 3 different seeds of this multi-layer perceptron I just described. We looked at a somewhat larger multi-layer perceptron where the first hidden layer is twice the size, 1024. Then we looked at a a small convolutional network, mini AlexNet, which has, I believe, 2 convolutional layers. So the test accuracy is considerably better than for these perceptrons. And we looked at 3 pre-trained networks, AlexNet and 2 variants of VGG, which were pre-trained and which were trained on the larger ImageNet dataset, which has 1,000 classes. So we trained for 100 epochs, initialized with a low uniform distribution. I'm going to say something about the singular value statistics in a moment, described by the Marchenko-Pastur law. We had a exponential learning rate schedule. We trained with momentum and a mini batch size of 32. And for the convolutional network, we trained with L2 regularization with a strength of 10 to the minus 4. But these multi-layer perceptrons were trained without regularization. So the basic idea is to decompose the weight matrices according to a singular value decomposition, where one has a product of 3 matrices. 2 of them, these matrices V and U, are orthogonal, and sandwiched between them is a diagonal matrix whose elements are the so-called singular values. And before training, either for a random IID Gaussian distribution of entries or Gloro uniform, it doesn't matter. The singular values follow the so-called Marchenko-Pastur law, which essentially is a Wigner semicircle for the square of the eigenvalues. And it has a left and right boundary, which are denoted by mu min and mu max. And this mu min and mu max are known, so they depend on the variance or the standard deviation of the entries of the random matrix and on the aspect ratio, so on the number of rows m and columns n that determines the shape. And what is shown here is the distribution for a square matrix, 512 by 512 entries. So the red curve is an empirical distribution computed for one particular realization of such a square random matrix. And the dashed curve is this Marchenko-Pastur law. And so there is quite good agreement between the two. And the basic idea is now, if one computes the same singular value distribution after training, so that's the blue curve, large singular values appear, which were not present before training. And the small singular values still approximately follow the form of a Marchenko-Pastur law, however, with a reduced normalization. So the total number of eigenvalues in this Marchenko-Pastur regime is smaller now. And this way of looking at network matrices has been also used by other researchers. So there is a work which predated ours by Martin and Mahoney. And Brice Ménard looked at this problem from a somewhat different perspective. That's very interesting work. So he thought about representational alignment, and I hope we will hear a detailed talk about these results. So the basic idea is that there may be learned information about the CIFAR-10 dataset stored in these large singular values, and that's the storyline which I'm going to follow in a moment. But before doing that, I will look at another quantity which lets us conclude that even for trained weight matrices, these small singular values are random, and that's the so-called nearest neighbor spacing distribution. So in order to extract the spacing distribution in a universal way, we first have to get rid of the averaged density of states of these singular values. So we first define a smooth version of the density of states, and this is by summing over Gaussians which are centered at given singular values. And we use a window of 21 of such singular values to get this smooth version. And then essentially one has to divide out this average singular value density to normalize the spacing on average to 1. And in random matrix parlance, this is called unfolding. So first one computes the cumulative distribution from the smooth version of the density function. And then one can define the unfolded singular values by inserting the actual singular values into this cumulative distribution, which is multiplied by the number of singular values. And after doing so, one finds that there is very good agreement between the empirical spacing distribution. So S are the spacings normalized to 1, which has a probability density, which was first computed by Eugene Wigner. It's a so-called Wigner surmise, and it's a product of a Gaussian part and a linear part. And this linear part tells us that small singular value spacings are very rare. And this is an effect known also as level repulsion, which is characteristic of neural network matrices. So we quantified the agreement between this empirical distribution and the Wigner surmise using a statistical test, the so-called Kolmogorov-Smirnov test. And we found that the hypothesis that it's described by the Wigner surmise cannot be rejected even at a 40% confidence level. So in the following...
Can I ask a question?
Mm-hmm.
If you look, do you also see, so this is a statement about the short distance level repulsion.
Mm-hmm.
Do you also see like long distance effects like spectral rigidity or
Yes,
any of those things?
Tested for that as well. And we do not find systematic deviations from random matrix behavior.
Okay, even at long distance. Cool.
Even at long distance, yeah. So I briefly want to talk about this Kolmogorov-Smirnov test because I'm going to use it to characterize the distribution of eigenvector components a lot in the following. So I want to make sure that it's clear what I'm using. So it's a non-parametric test for comparing empirical distributions with a theoretical model. In particular, it compares two cumulative distribution functions in the following way. So there's the empirical cumulative distribution functions for n observations, which is indicated by a step function here. So whenever one hits an empirical observation, the cumulative probability goes up by a step. And then there is a model distribution function f0, which is shown by the red curve here. And what one looks at is the supremum of the distances between the empirical and the model distribution function. So this is the test statistics dn. And the important result is if one rescales this test statistics by the square root of the number of observations, one obtains a universal distribution, the Kolmogorov-Smirnov distribution. And now one can make statements about the validity or likelihood of a null hypothesis, which would be that the two distributions are identical, that the empirical observations are really drawn from the model distribution. And this hypothesis can be rejected, as one may imagine, if the distance between the model distribution and the empirical distribution becomes large. And this Kolmogorov-Smirnov distribution allows to compute threshold values for a confidence level alpha, which are computed by demanding that the probability that this random variable is less than 1 minus alpha. Okay, so one wants to exclude accidentally poor agreement between the model distribution and the empirical distribution. So that's the way how this Kolmogorov-Smirnov test is used traditionally. So we are going to use this quantity in a slightly different way. So we characterize the empirical distribution by a p-value which is computed by asking what is the probability that the deviation is even larger than the observed deviation. So if we find a p equal 1, it implies that there's absolutely perfect agreement between the empirical distribution and the model distribution. And in general, if the data are described by the model distribution, then p is uniformly distributed in the interval between 0 and 1. And what we are going to do is we are going to average several of these p-values. And this implies that this average will concentrate at the center of the interval. So it will have an expectation value of 0.5, and the variance will become smaller due to this averaging. And that's a quantity which I'm going to use in the following to characterize singular vectors. So the idea is that random matrix theory also makes a prediction for the singular vectors of W, which can be obtained by computing the eigenvectors of W transpose times W. And they are predicted to follow a Gaussian distribution whose standard deviation is given by 1 over square root of the number of components of the eigenvector. And so due to the fact that this p-value fluctuates a lot, we average p-values over a window of size 31 in this case. So we have 512 eigenvectors in total, and we have this window size. And what one finds then is that for small singular values, this p-value is relatively large, which indicates that these eigenvectors are mostly random. Whereas for large singular values, this p-value drops, indicating that there are systematic deviations between empirical eigenvectors and this Gaussian distribution. And I want to spend the following minutes to argue that there is indeed learned information contained in these singular values and associated singular vectors, which was obtained during the training of the network. But before doing this, I want to mention that there is another way of characterizing singular vectors and their agreement or disagreement with those of random matrices. That's the so-called inverse participation ratio, which is the sum over the fourth power of eigenvector components, assuming that the eigenvector is normalized. So let me briefly explain the intuition behind this. So let's consider two examples. One, where all components of the eigenvector are of equal magnitude. So due to normalization, it would be 1 over square root m. And in this case, this inverse participation ratio is 1 over m. So it's 1 over the number of significant components in this vector. And all components are significant, so there are m significant components. It is 1 over m. Whereas in the opposite case, where only one component of the eigenvector is 1 and the others are 0, this inverse participation ratio is 1, which again is 1 over the number of significant components of the eigenvector. So if the eigenvector is random, we should be close to this case where all components are of comparable magnitude. And this is found in the center of the spectrum. So all these examples are for the second hidden layer of this three hidden layer perceptron. And here a comparison is shown between this p-value, where deviations for large singular values are found. And this is also the regime where this inverse participation ratio becomes really large, indicating that there are relatively few relevant components. Okay, so this backs up the conclusion that something interesting is happening for the part of the spectrum where we have large singular values.
All right, I have a dumb question. So here you've got like 512 component vectors, and you've normalized the eigenvectors. So like there's a definite prediction for what the inverse participation ratio is if they were just Gaussian random components.
Yes, exactly.
Right? Does that agree with that 6 or 7 or whatever
yes,
you find? Okay, great.
This part. Okay, now let's look at this distribution for different networks. So this upper row is the second layer of the somewhat larger multi-layer perceptron. So this behaves essentially in the same way as the example I had shown previously. Here I show the first dense layer of the larger convolutional networks. So it's a dense layer, not a convolutional layer. And the difference here is that there are deviations from the random behavior, both for small and for large singular values. And also the signal in this inverse participation ratio is stronger for small singular values than it is for the multi-layer perceptron. So this indicates that there may be information stored in small singular values. So that's an idea which I will come back to when discussing large language models in the end of the talk. And here are results for convolutional layers of the mini AlexNet, which we trained ourselves. So the convolutional layer is blue. And again, it indicates that there may be deviations for both small and large singular values. And there's a dense layer shown in orange, which behaves very similarly to the hidden layers of the multi-layer perceptron, that there are statistical deviations for large singular values. Okay.
Bernd, just 1 second. I just wanted to understand, so the IPR, ideally, if everything was random, should be completely uniform across the singular value position. Is that right?
Yes, it should be in this region of 6 here. So I think it's about 3 times what one would get if they were all identically equal. Yeah. Mm-hmm.
I see. And how should I interpret the left plots?
The left
what is
part,
that telling me? Like,
that's
yes,
this,
exactly.
that's something like a probability that the distribution of singular value components agrees with the Gaussian, loosely speaking.
I see. Okay. And this is using the test that you explained before,
this test statistics, this Kolmogorov-Smirnov test statistics, which I described before. And it's just strictly speaking not correct to say that this is a probability for agreement. It's a somewhat looser usage. Yes?
Is the reason why you're not seeing in the p-value any deviation from randomness at small singular value just because the chaos test uses the cumulative distribution function? And
we did not delve into this deeply.
Okay.
Why there can be differences between.
I guess you'll talk about the small singular values later, because
I mean, there's still a slight drop, right?
Yeah.
So that's
I see what you're saying. Okay.
And it's still a slight drop, so it's qualitatively consistent, the two observables.
That wouldn't explain the difference between the VGG net and the other network, which is what I'm curious about. How do you, well, and I suppose you'll get to that. How do you characterize the ones where you see an effect at small singular values as well?
So we did not look into this in detail for the image recognition networks. We looked into this in detail for the large language models. And there I'm going to present evidence that the small singular values do contain information, and that in particular, they contain information about fine-tuning of the model. But that will be the bottom line of the end of the talk. Okay.
So can I ask something sort of related? There's a notion that the trained model kind of localizes on enhanced symmetry loci. Does that relate to this, or how does that relate to this way of organizing the trained model information?
So the enhanced
that makes a lot of sense. Like an approximate zero eigenvalue would be.
So it would be a symmetry of which quantity?
It would be like a permutation symmetry of the nodes.
Yeah, but permutation symmetry of the nodes you always have. I mean, but what I can say is that the permutation symmetry of the nodes turns into an approximate rotation symmetry of the model if one is close to a minimum, and that has consequences for the Hessian matrix. So we have another work upcoming where we study this, but I'm not sure whether.
I guess maybe Eva's question is the number of meaningfully small singular values
Mhm.
equal to the dimension of the space of rotations that are approximate.
So I think this interpretation is true if you look at the spectrum of the Hesse matrix, but that's a spectrum of the weight matrix. So for the Hesse matrix, it indeed turns out that one, say, can count the number of generators of the rotation group and compare that with the number of small singular values of the network. But that's for the spectrum of the Hesse matrix and not for weight matrix spectra.
Actually, I had a question. I mean, maybe you can connect all of this to the Hessian matrix spectra. So a naive model would be once you get to the minimum, the loss landscape is quadratic, so it's characterized by Hessian. And then you can characterize the random weights as a Gibbs distribution on the random weights with a quadratic energy function given by the Hessian.
Yes.
So then the spectrum of the Hessian will control indirectly through random matrix theory the spectrum of the singular values of W, right?
Yes.
So could you measure the spectrum and make a prediction about the singular value spectrum of W from the Hessian?
So in principle, yes. So there is the notion that the spectrum of variances of weight fluctuations is proportional to the spectrum of the Hessian. And we tested this and all of this works, but we have not done statistical tests to see whether these spectra are faithfully reflected in the weight matrices. But in principle, I completely agree. So yeah,
Yes.
yeah. And I'm going to briefly discuss random matrix models where the distribution of the randomness in the weight matrix is assumed to, or is taken from the distribution of eigenvalues of the Hessian and of the covariance matrix. So yes, there is such a connection.
I see.
Okay, now I want to back up all of this by systematically setting small singular values of these weight matrices to 0. So this on the left is again a plot of this p-value as a function of the singular value position. And on the right-hand side, we looked at the train accuracy of the model when setting a certain percentage of small to large singular values to 0. And one indeed sees that one can set up to 70% of the small singular values to 0 without affecting the train accuracy of the model. And this agrees roughly with the point where this distribution of p-values starts to drop. So this is, again, evidence that specific information is contained in those singular vectors which deviate from these random matrix predictions.
I had a question. If you remove them in a different order from largest to smallest, would that curve be then drop sharply as a function of the percentage removed?
Yes, it would. Yeah. Okay, so this is the train accuracy. Before discussing the test accuracy, I would like to introduce an interesting complication. And that is considering so-called label noise, where the pristine data set has been changed in the sense that the labels of images are partially or completely randomized. And this is motivated by an influential paper where the authors found that a given neural network can both learn the classification task, but it also can memorize incorrect labels. And so the question raised in that study was, how is it possible that the network generalizes if there is something to generalize, but that it memorizes if the only possibility is memorization? And so these are singular value spectra for the network being trained with different amounts of label noise. So the blue curve is using the pristine CIFAR data set, and then the green curve is 40% label noise, and the brown curve 100% label noise. And what one sees here is that neither the p-value nor the spectrum really allows to distinguish the addition of label noise in the training data. They look rather similar, which can be rationalized by arguing that after all, it's randomness which is injected into the network if the labels are randomized and so this additional randomness might not be distinguishable from the original randomness already present due to initialization. So I'm running a bit short in time, so I do not want to discuss in detail why these p-values somewhat increase in the regime of intermediate singular values. It turns out this has to do with the requirement of orthogonalization, that the singular vectors in this regime have to be orthogonal to the singular vectors with large singular values, and this gives rise to an increase of p-values, so that can be discarded. It's not an indication that there's information stored. Okay, so let me skip over this. Now, I first want to look at the chain accuracy again. And now one does see, when removing or setting to 0 singular values, one sees that in the presence of label noise, more singular values are needed to achieve a chain accuracy, that's the brown curve, than in the absence of label noise. So the hypothesis would be that there's an intermediate range of singular values which encode for these missing labels, and that maybe the large singular values have something to do with encoding specific features in the chaining data which are not related to labeling them correctly. And the same is, or it is true in a more striking manner, even if one looks at convolutional layers, a convolutional layer in this convolutional network, where one can remove 90% of singular values for the pristine data, but can remove only 30% of singular values for the randomized data. So that's sort of the place where all this additional memorization takes place. It's in the intermediate part of the spectrum. And so here are results for the test accuracy for different layers, but only in the absence of label noise. So these results confirm the idea that the information is stored in the large singular values. Okay. So far I presented only results for considering a single chaining scheme, chaining schedule, which I described initially. Now I want to argue that the results actually depend very much on the type of chaining schedule, and that in particular there's a big difference between feature learning, network chained in the feature learning regime, and the network chained in the lazy learning or NTK regime. So we introduced a parameter alpha, which appears both in the input to the softmax function, and it appears in the overall normalization of the loss. And it turns out that this combination of parameters allows to tune from feature learning to lazy learning without changing other aspects of the chaining regime, like the learning rate or batch size or things like that. So this is a plot of the chain and test accuracy as a function of this parameter alpha. So the blue crosses are the results for this multi-layer perceptron. So for all values of alpha, we reach perfect chain accuracy. And there is a slight drop in test accuracy when changing alpha. The full circles are results for a linearized network. And for large alpha, we see good agreement between the linearized network and the full network. And this is an indication that the full network is actually chained in the NTK or lazy regime. Okay, so that what I want to argue here is that alphas up to 1, so that's where we chained all the previous example networks, are in a feature learning regime, and that training with large alpha is in an NTK regime. Now we can look at all these observables as a function of alpha. So alpha equal 1, that's the data I showed you before, and that's even a plot for this number variance, which Alex asked about, these long-range statistics. In the rich learning regime, the spectra look very similar, but these p-values now drop also for small singular values. Okay, so that's a first interpretation that this drop for small singular values may be related to having a strong feature learning, whereas in the lazy learning or NDK regime, the singular value distribution stays unchanged and the p-values agree with the random control. So the argument I want to make here is that looking at the singular value spectrum and these p-values allows to identify the regime in which the network was trained. So if it's lazy, then the statistic stays close to random. And if it's feature learning, then one sees something both in the spectra and in these p-values. And when removing singular values, there's an important difference between feature learning and lazy learning. So if the network is in the feature learning regime, one can remove a relatively large percentage of singular values without destroying the test accuracy, whereas in the lazy learning regime, the information is equally distributed all over the spectrum, and there's an almost linear decrease in test accuracy when removing singular values. Okay, so this idea that the information is contained in the large singular values and singular vectors is true if the network is trained in a feature learning regime, and it can't be true if the network is trained in the NDK regime or lazy learning regime. So now I want to come back to this modeling in a late phase of training, where we assume that the network matrix is the sum of a low rank part with information and a random part. And in this case, the singular values of the low rank part get shifted due to the noise which is added. For the case of Gaussian distributed noise, this was worked out in the literature before, and one can compute the shift. So what is shown here is a spectrum, the blue with the empirical eigenvalues, and the red ones are the shifted eigenvalues according to the theory, where one reconstructs the eigenvalues of the signal matrix from the eigenvalue of the full matrix. So this tells us that adding noise has a rather big effect on these eigenvalues. So this is for 40% label noise. And we indeed could demonstrate that so the blue curve is about removing eigenvalues in the presence of 20% label noise or 40% label noise, that already removing the small eigenvalues increases the test accuracy. So that's in agreement with the idea that this label noise is stored in intermediate eigenvalues. And when in addition shifting the singular values according to the theory I just described, that's the green curve, then one has an additional increase in test performance. So this is a first indication that this idea has some merit, that for a trained network, the weight matrices have an information part which is low rank and a noise part. We did this more systematically and looked at the increase of the test accuracy when removing singular values, and for larger amount of label noise, this indeed helps in increasing the test accuracy. So this is nice in the sense that it gives credibility to this idea that there is noise in the spectrum and that removing it can be helpful. I should add, though, that it's not a state-of-the-art network, not a state-of-the-art method for training networks in the presence of label noise. There are more powerful, specialized methods for doing this. Okay, so I'm running a bit late, so I'm going to skip over this part where we developed a filtering algorithms for a situation where the noise has a power law distribution. So that's what Surya mentioned. So one can develop random matrix estimators for this shift in the presence of label noise, but I would want to say a few words about transformer architectures. So these are mostly analytical calculations for this eigenvalue shift. And now I want to start with the analysis of transformer or architectures. So we looked at two pre-trained transformer models, a BERT model, specifically the BERT base uncased, and I'm showing results for the singular value spectra of two types of matrices in layer 11. So it's an attention output matrix, which is very close to the random matrix behavior, indicating that it's maybe in the lazy learning regime since it shows so little deviation. And that's a result for the query matrix in the same layer, which has significantly stronger deviations from this random initialization. We also looked at the Llama 8B model, which has significantly stronger deviations from the initial distribution, indicating that it's much more in a feature learning regime than this BERT base model. So in addition to looking at individual layers, we also averaged the probability distributions over all layers. So this is shown here. And the results are qualitatively similar, that the BERT model has maybe less feature learning than the Llama model. So we also looked at the agreement of singular vectors with this Gaussian distribution, which is characterized by this p-value. So large p-value is good agreement. And now we use the labeling a little bit. So what were previously large singular values are now small indices. Okay, so the largest singular value has the smallest index and is now on the left-hand side. So that's for the query matrix. So the blue curve is an individual query matrix, and the orange is the average over all blocks, indicating that there may be information in large singular values and vectors for query matrices and attention output matrices, but there is a somewhat different result for intermediate dense matrices. So they belong to the fully connected layers following the attention blocks. And I want to make the argument in the following that this is indeed an indication that important information is stored in these small singular values in the fully connected layer. So one quantity which we also looked at for comparison is the covariance matrix for network activations. So the X are the activations of neurons, and they are averaged over all input tokens. And this is a symmetric matrix, has orthogonal eigenvectors, and we looked at the agreement between singular vectors and the eigenvectors of this activation matrix. So the idea is that if there's interesting input coming into a given layer, then the network matrix should have adapted to this input such that it is able, that it's aligned with the input and is able to process this input. And we quantify this by considering the maximum of the dot product for a fixed singular vector, and we take the maximum over all possible vectors of this covariance matrix. And now here I want to argue that there's agreement between these three different measures. So we have the singular value distribution, which shows deviations both for small and large singular values. We have the p-values, which drop for both small and large. And we have an increased overlap or an increased alignment between this covariance matrix of activations and the singular vectors. Okay, now comes the demonstration. So what we did here is we divided singular values into deciles. So 10 blocks containing 10% of the total number of singular values, and then set to 0 a given block, a given decile. So going from small singular values, which would be 10, to large singular values. And we did this only for specific types of matrices in the transformer. So here it is shown for query matrices. So the behavior of the p-values indicates that the large singular value should be particularly important, and one indeed finds a big performance drop if the large singular values are removed, and very little performance drop when the small singular values are removed. Whereas for the intermediate dense layer, which I discussed a few times previously, which has this drop in p-value for the small singular values. There is now also a drop in performance if these small singular values are removed. Now you could argue, when looking at this a bit more closely, what about these key matrices? There is a huge drop in p-values, but it doesn't matter to remove singular values. So we found that this depends a little bit on the type of test. So what we used here is the Boole Q dataset of the superglue benchmark, where the small singular values did not have an effect. When looking instead at a different test, this word in context benchmark, then removing the singular values does have an effect. Okay, so the bottom line is that these transformers are quite complicated and that a given benchmark might not test all the capabilities which are present in a given model. Okay, now the last part. So here we are comparing setting singular values to 0 and fine-tuning afterwards, or fine-tuning first and setting then singular values to 0. And it's again the same deciles. So these are setting the 10% smallest singular values to 0, and this is setting the 10% largest singular values to 0. And one sees that when fine-tuning afterwards, it is okay to set small singular values to 0. But when fine-tuning first and reducing then, there's a significant performance drop when setting the small singular values to 0, indicating that the fine-tuning information is stored in them.
Bernd,
And-
I don't want to derail you because we want you to get to the punchline, but I would like to ask you exactly what do you mean by fine-tuning?
Okay, so there's the pre-trained BERT transformer, which can be downloaded from Hugging Face. And then in order to evaluate it on the superglue benchmark, it needs to be fine-tuned. So there's a training data set. So this Boole Q, for instance, is I think it's yes, no classification of whether the answer to a given question is correct. So the transformer is presented a question and an answer, and it needs to decide whether the answer is correct. And the pre-trained model is not able to do this. And then one performs fine-tuning, and we use the so-called LoRa algorithm, where one adds a low-rank matrix to all the transformer matrices to enable it to solve a specific problem at hand. So that's what fine-tuning means in this context.
Thank you.
And this apparently is stored predominantly in the small singular values. And with this, I want to conclude, arguing that random matrix theory is helpful, but also that I think there are interesting avenues for further research. So one avenue might be to think about estimators, which systematically remove the effect of label or training noise and in this way improve networks. But I think it may also be interesting to locate specific information in transformer networks, for instance, by partially destroying the hierarchical order or certain properties of the training data. Sort of the analog of randomizing the labels in the CIFAR data set, that one, say, destroys causality in the training data and then looks where do the spectra change and where is causality encoded, perhaps in such language models. So I would like to thank you for your attention.
Thank you, Bernd, for the great talk and the great timing. So, more questions?
Hi, I have a quick question. So does this give you a prescription for what rank is sort of optimal for your neural network weights in the, let's just consider the MLP case. So can you use this theory to determine a priori what rank I should?
I think that's an interesting open question. So I do not have a definite answer to this, but I have a guess. So my guess is the following. if you start with a let's say hypothetically that you can determine the quote unquote necessary rank or necessary size of a network matrix by looking at this number of deviating eigenvalues. And then you could think about using a smaller network size from the beginning. But my suspicion is then that training might not work because there might not be sufficient alignment between the randomly initialized singular vectors and the eigenvectors of the data covariance matrix. But I think that's a question for future research as well. So one might try, for instance, to pre-align the network weight matrix vectors with the eigenvectors of the data covariance matrix and then get away with training smaller networks from the beginning. But that's pure speculation at the moment. Yeah.
Paul, your question?
Oh, I think you may have just answered it, but I'll just repose it. We talked about this last summer and also with Greece the summer before last. Just this question of you look at the spectrum and you've got these enormous resources to train this gigantic network on this huge amount of data. And then what you're essentially indicating to us is this broad middle ground of the singular values has no information whatsoever. It's just singular. And so are there, and I know this would almost be the holy grail, so I'm not expecting a direct answer, but do you have possible protocols for avoiding all of that excess labor and focusing right in on, training directly the singular values you need?
So I think it's a related question, and so my answer is similar to the previous answer. So what I would try is study the input data covariance matrix. And okay, so it's known that the eigenvalues follow a power law. So there is no clear separation between what needs to be kept and what can be discarded. But one could still try to initialize the network such that the singular vectors of the initial network matrix are already pre-aligned with eigenvectors of the data covariance matrix. And in such a situation, I could imagine that one gets away with using, with training smaller networks. But that's something which we want to try out, or which other people in the collaboration can try out. I think it's something for the future.
One addendum question. In our previous grant proposal, there were also various suggestions about ways to remove redundancy in the training set, that in some sense, we just throw everything at it, but there are diminishing returns. And it would be nice to, in the presentation to Simons, there was talk about you do it once and put a lot of effort into, reducing down the training set, but it has all of the essential information. Do you see any clues to doing that in this singular value decomposition?
So we have not looked very much into singular values of training sets. I think that's more things Julia Kempe talked about, that if I remember correctly what she said, that it's the really rare elements of the training data set which are important for the power law tails of the scaling laws. And I believe what she said is that if one keeps these rare examples, then it may be possible to remove some of the more frequent examples. But I don't see that the types of methods I talked about today would be helpful immediately in showing this.
Okay, well, great. I missed her talk because I had a conflict, but I believe it's recorded, so you've now given me incentive to go back and listen to it.
I actually had a question. I mean, so I think you argued quite convincingly that large singular values and vectors contain information about training data. But what information? I mean, can we use, say, attribution analysis to go back to
Mm-hmm.
if you change the training data, how would you change it to change the singular vectors
Yeah.
or something like that?
So we haven't done this yet. So the only partial evidence I have is that there seems to be an alignment between singular vectors of the network matrices and eigenvectors of the activation covariance matrix. And so when going to the very first layer of the network, then
I
one
see.
could hypothesize if there's a similar alignment that one would learn sort of the features of the training data.
So in a
in
linear
vectors.
network, oh, I see. In a linear network, wouldn't that be exactly true? I mean, if y is w times x, oh, I see the x plays a role there. I see. Okay, that's interesting.
Yeah, and I think it would be an interesting question for future research, say, comparing how the space of dominant eigenvectors of the activation matrix changes if the information passes through the layers.
Yeah.
And whether it stays in the same subspace or whether the subspace is somehow rotated a bit.
Yeah. I see. I suppose you could align to the data in the following way, right? So let's say you have the activation matrix, which is neurons by data points, right? You're looking at the covariance of the activation, so you're looking at the I don't know, left or right singular vectors of that matrix. But you could look at the other singular vectors, which are singular vectors over data points, and you could see what functions over data points those are, right?
So that would be the kernel, right? If
That would
the
be that would
indices
be the
are,
kernel, yeah, exactly.
but I wouldn't know how to match information from this kernel, which lives in the space of data points, to the network matrices, which live in the space of neurons.
But that's just the pairing of left and right singular vectors, right?
Ah, okay. Ah, that's a good point. Yeah, you're certainly right about that.
Yeah, so it might be easier to interpret as functions over data points rather than as functions over neurons.
Yeah, that's an interesting point.
Bernd, that was a great talk. I just wanted to understand better, like you said in the intermediate layers of a transformer, the smaller singular values start to encode information. And do you have a sense for why in that part of the architecture, like the smaller singular values start to like matter more than like the larger ones?
Yeah. So it's the intermediate dense layer of the fully connected part, right, of a block. I do not fully understand it, but I have a partial argument, and that has to do with the matrix dimensions. So key and query matrices are square matrices, which means that the Marchenko-Pastur law extends all the way to 0. And it's really difficult to have the concept of small singular values, whereas this intermediate dense matrix is rectangular. And so the Marchenko-Pastur law has a lower bound at a finite non-zero value. And that's a reason, at least a formal reason, why one can clearly identify deviations for small singular values. But this can't be the full story, because we looked at setting singular values to 0 and did see a difference all the same. So the answer is I don't really know why it appears in the fully connected layer and not in the attention part.
And you said when you were doing the fine tuning, you were doing specifically low rank fine tuning. Did you try doing full rank fine tuning and see if that had any difference between like which singular values were affected?
So we stopped this full rank fine tuning rather soon, because our interest was in reducing matrices, and that doesn't commute very well with reducing matrices. So I don't really know that. And it's also less efficient and takes longer. No, so I do not know the answer to that.
Okay, thank you.
one facetious question. Is there a reason why you confused us by switching the ordering of the singular values from the image networks to the language networks?
Okay, so it's what first is what other people did. So I mean, there's a literature about pruning of transformers, and we looked into that literature and tried to see whether random matrix theory might help with a better model reduction. And the answer to that is one cannot do a lot of model reduction. Okay, so I showed you results for removing 10% of singular values, and we went up to removing 20 and 30%, and things went downhill rather rapidly. And our interpretation is that there, at least in this BERT model, there are lots of layers in the NTK regime, and that removing eigenvalues from these layers, which are flagged as random by the types of tests we are using, destroys the model performance. Yeah, so it's convention. And the second thing is that some of the matrices have really large outliers that it would have been difficult to plot.
Making connection to what other people have already done on those models makes perfect sense.
Yeah.
All right. So if there are no more questions, let's thank Bernd again.
Okay, thanks for
And
listening. Interesting questions.
and we will meet next Friday if we find a brave volunteer.